Hi everybody. Lecture 26 of Applied Statistics is an introduction to statistical process control, which is a part of the larger subject of statistical quality control. We're going to limit ourselves in this introduction to looking at control charts for means and for ranges. The lecture is going to start out kind of general with very descriptive kinds of ideas and looking at the basic idea of a control chart. As we go on, we're going to get more mathematical. At the very end, we'll look at some technology, Mathematica, and a spreadsheet. Here's the lecture plan. So first, we'll look at general principles behind statistical process control. Again, this is one aspect of quality control. We'll look at, in particular, control charts. We'll start with the main idea of a control chart and three special lines in the chart, the LCL, the CL, and the UCL. The LCL stands for lower control limit. The UCL at the top stands for upper control limit, and the CL is in the middle. It doesn't stand for control limit, it stands for center line, even though it's not actually always in the center. We'll look at also what its ideal properties are. We'll look at sample mean control charts, first in theory, but ultimately in practice. What kind of form do they have? What do they look like? How are they constructed? Especially what are called 3 sigma control charts. We'll look at briefly the relationship of these charts and how to use them to hypothesis testing. We'll look at run length distribution and expected value. In other words, how long will it take until you see your first out of control observation on average. We'll look at the relationship to the sample range, and here's where we use Mathematica to verify some things that will seem kind of mysterious if we don't use Mathematica. Then we'll finally look at the various relevant formulas to actually compute these things. And then we'll look at sample range control charts and the various relevant formulas before finally at the end looking at an example, how to construct control charts in a spreadsheet. I'm not going to go through the entire construction because it would take a while. I'll show you the finished product. I'll show you some of the formulas that I use. So what is statistical process control? We want to make manufacturing and business processes stable over time. That's the big overarching idea. All processes, no matter what, in business and manufacturing, if you're making something, if you are doing something, if you are designing a product, have some variation in, for example, costs or how long they take or how something is made. We want to control this variation. That's the idea, big idea behind this. We want it to be within bounds and be random in nature. You can't completely control it. You can't make it always the same. It will not always be the same revenue you get from a certain kind of advertisement. It will not always be the same size of the product that you make. There will be microscopic deviations, but we want to control those things. Random variations are sometimes called common cause variations because they occur in all processes. It's common. Random human error, that kind of error could be in just doing something wrong or taking longer than usual to do something or shorter than usual. Random measurement error, etc. The idea about random things is they are common to all things and they are measurable in a sense. You can get an idea about approximate sizes of random errors. We can contrast this with what are called assignable causes or special cause variation that occurs because of the normal functioning has changed in some systematic way. Maybe the machine that is manufacturing some part is malfunctioning for some reason that we hopefully can identify. A process that continues to be described by the same distribution when it's observed over time is said to be in control, whereas sometimes they're out of control. Control charts are used to monitor the process and alert us to when the process has been changed so that it is now out of control. Now, first of all, you should realize that out of control doesn't necessarily mean something is wrong, but you might say it's likely to be wrong. So this is a signal to us to find and correct the cause of the change, if there is a cause and if it can be found. What are control charts? Well, sometimes they're called Shewhart control charts after the person named Shewhart who first came up with them. They can again help us distinguish between common cause variation and special cause variation. Here's an example of a generic control chart. You see the horizontal axis is the sample number. Sometimes that's called the subgroup number, starting with 1, 2, 3, etc., and in this case going up to 20. And the second coordinate of all these points is the sample mean. We are looking at a bunch of different random samples. Each of these samples is a sample of a certain size. Typically 4 or 5 is a common kind of sample size to use. In each of those cases, we're computing a sample mean. For example, with this first one, the sample mean is somewhere around 70. With the second one, it's slightly less than 100, etc. We're making this plot. You see the LCL, lower control limit, the UCL, upper control limit, and the CL, which is the center line. The process is out of control when the sample mean is above the UCL or below the LCL. In this case, you can see this particular observation, which is sample mean number 17, is above the UCL. Then we say the process is out of control. We get a signal that something might be wrong and we should investigate. What are some ideal properties of control charts? Well, first of all, they should be simple. Okay, hopefully that kind of graph that we just saw in the previous slide, this is a fairly kind of simple thing to see. When you get the part of the graph going above the UCL or below the LCL, you are alerted to something possibly being wrong. You want to investigate. A second property that control charts should have is they should allow for the detection of an out-of-control situation quickly. Once it gets above the UCL, once it gets below the LCL, you stop the process right there and investigate. Third, they should have a low false alarm rate. In other words, we do not want to call a process out of control when in fact there's nothing wrong. False alarms are costly. If you know about hypothesis testing, this is similar to making a type 1 error where you reject the null hypothesis when it's in fact true. The null hypothesis here would be that the process is in control, and you're rejecting that, saying it's out of control when it's really in control. And finally, they should work well with small samples, hopefully samples of size 4 or 5 as are commonly used. So let's get into the details now of what mean control charts are and how they are constructed. Mean control charts are an example of variable control charts because they involve taking means of quantitative variables, as opposed to attribute control charts, which are related to counts and corresponding proportions for categorical variables. Variable control charts are devised, like I just said, for monitoring quantitative variable measurements. This includes monitoring both the mean, the central tendency, and also it's important to monitor the variability of a process. We can certainly measure the variability of the process, as usual with the standard deviation or the variance. Historically, however, with control charts, the range has been more commonly used, which is the difference between the highest value and the lowest value, the max minus the min. Obviously, this is because the range is much easier to compute quickly without technology, especially for small sample sizes. Just as obviously, however, we now have the technology to just use the standard deviation without slowing down our use of the charts. Okay, so we could do the more complicated thing with standard deviations, but for this lecture, we're going to just keep it to the historical approach with the range. A control chart to monitor the mean is centered at some target value, call it mu sub 0. This notation is analogous to what you would see in a hypothesis test for the mean, where the null hypothesis H0 is that mu, the population proportion, is equal to some specific number, call it mu sub 0. This defines the center line CL in the control chart, so that's in the center. The lower control limit, the LCL, is below it, and the upper control limit, the UCL, is above it. These represent the minimum and maximum values that the sample mean can assume without raising an alarm, in other words, without sending you a signal that something might be wrong. If x bar, the sample mean, is between the LCL and the UCL, then the process is assumed to be in control or operating correctly. That's an assumption. It's also limited. It's limited in the sense that it's saying the mean value appears to be close to the target, mu 0. Note that this does not guarantee that everything is fine with the process. It does not guarantee quality of your final product, for example. Otherwise, if the sample mean is not between these limits, the LCL and the UCL, we have a signal, an alert, an alarm, that the process mean is not where it should be. It's shifted away from the target mu 0. Ideally, we'd like our LCL and UCL to be of the form, in this case at least, the CL, the center line, plus or minus some constant. And that constant is typically thought of as being a multiple, k times Sigma sub x bar. So here we're starting to get a little bit more mathematical here. Hang on. What's that? That's the standard deviation of the distribution of the sample mean, sometimes called a sampling distribution. Typically it's a normal curve, and it's representing how x bar, the sample mean, varies over many, many samples. We want it to be some multiple of that as far as the margin of error, so to speak, in this control chart. Most typically, we take that multiple, that k, to equal 3. Then it's called a 3 sigma control chart. Sometimes we take k to be 2. Then it would be a 2 sigma control chart. All right, now we're going to get even more mathematical. This is an advanced statistics course. Just try to get the big picture if you don't know the advanced math. Try to understand the big idea. I'll try to explain it in intuitive terms. If x, the variable we're measuring, happens to have a normal distribution, that's what the capital N here means, so it's a bell-shaped distribution, with mean mu0, we're assuming the process is in control when we say that, and variance, sigma squared, that's measuring the variability, that would of course mean the standard deviation itself is sigma, which is something you're more used to doing. This is our standard notation to put the variance in the second spot. Some people put the standard deviation. If that's true, we know that x bar, the sample mean as a statistic, as a random variable, also has a normal distribution, in fact with the same mean mu0, but with a variance, and therefore a standard deviation, that's smaller. We need to take the original variance, sigma squared, and divide by n. Okay, when the sample size is large, the values of x bar don't vary as much from sample to sample. That's the intuitive idea there. That's intuitively why we divide by n. In addition, something called the central limit theorem implies that when n is quote-unquote large, x bar is quote-unquote approximately normal with the same mean and same variance as the previous line, even when x itself does not have a normal distribution. In statistical process control, it is typically assumed that the variable capital X is close enough to having a normal distribution that large includes sample sizes as small as n equals 4 or n equals 5, which are the most typical kinds of sample sizes to use. These are the common sample sizes for the subgroup samples that are taken periodically when we're making control charts. Pretend in a manufacturing process, maybe you make these charts once an hour, say, based on samples of size 4 or 5. We therefore assume the following probability statement is a good approximation. The probability that x bar, the sample mean, is within 3 x bar standard deviations from mu0 is about 0.997. Have you heard of the 68, 95, 99.7 rule before? It says that with a normally distributed variable, about 68% of the probability, or 68% of the data, if you gather data for that variable, is within 1 standard deviation of the mean, 95% is within 2 standard deviations of the mean, and about 99.7% is within 3 standard deviations of the mean. That's what this is saying as a probability statement. The chances that a given sample mean x bar from the sample of, say, size 4 or 5 is between mu0 minus 3 standard deviations for x bar and mu0 plus 3 standard deviation for x bar is about 0.997. In other words, for a process that is in control, if we assume it's in control, a false alarm of saying, hey, it's out of control when it really is in control will only occur with probability 0.003, 1 minus 0.997, which is 0.3%, which is the same as 3 out of every 1,000 samples. Okay, so not very often. We don't want those false alarms, remember. At least not very often. False alarms are also related to hypothesis testing. This is my brief connection to hypothesis testing beyond what I've said so far. They're essentially type 1 errors of the following test, where the null hypothesis is that mu equals mu0, and the alternative hypothesis is that mu is not equal to mu0. By rejecting the null, essentially, when the null is true, we're making a type 1 error. That's the same as a false alarm. Since we may be obtaining hundreds or even thousands of samples and their corresponding values of x bar, as we do this process and make the control charts, eventually it's a guarantee that the process will be signaled as out of control, even if it's truly in control. Okay, that's going to happen. When something has a small probability, it is unlikely to occur on any given trial. However, over many, many trials, say hundreds or thousands in this situation at least, it will happen. Okay? How often? Well, let's let capital Y be the number of samples of the same size. So again, we're talking about samples of size n, where n might be 4 or 5 most commonly, until the in-control process, in reality it's in control, will be erroneously identified as out of control. Understand the idea here? So Y could take on whole number values. It could be 1, it could be 2, it could be 3, it could be 4. If it's 5, for example, then it took 5 runs of the process where we were sampling and computing X bar until we were out of control. Assuming independence of each sample, Y has something called a geometric distribution. So again, we're getting kind of mathematical here. My students know about geometric distributions. If you don't worry about it too much. With probability P of quote-unquote success on each sample. Where in this case, success is a bad thing, you might say. It means the process is identified as out of control. Success or failure in this kind of situation are just labels. They don't have to, success doesn't have to be a good connotation. Failure doesn't have to be bad. Okay, they're not maybe the best labels, but they are historically what people use. For a 3 sigma control chart in sufficiently large sample sizes, P, by the previous slide, will be about 0.003. The probability that X bar will be between the LCL and the UCL when the true mean of X bar is mu0 is 0.997. 1 minus that, 0.003, is the probability of being identified as out of control when in reality it's not out of control. And that results in a probability mass function, although my students know that our book calls those probability density functions, even though with the discrete case it's better to call them probability mass functions, that equals this. Okay? Now again, if you're not a very mathematical person, don't worry too much about what this means, and how it's derived for that matter, other than knowing you could use the formula to figure out the probability that, for example, capital Y equals 5 by substituting little y equals 5 into this formula. And the mean expected value of Y is 1 over P, which in this case is 333 approximately. Think of it intuitively. Imagine you're counting how many trials you have until your first success at something. Say baseball. Say you're a baseball player and say you're a bad hitter. Your probability of success, where success in this context really means something good, you get a hit, would say be 200, 0.2. 20% of the time you get a hit in your official at-bats. If that's your true batting average, 0.2, you would expect 1 over 0.2, which is 5 at-bats, official at-bats, before you typically get your first hit. Does that always happen? No, you could get 2 hits in a row. But 5 is on average how many trials that you have until you get your first success. We can expect to get a false negative in this context about every 333 samples or so, where this is very rough. The or so could probably be taken to be as wide as a range of 250 to 500 or even larger. For example, 1 divided by 0.002 is 500, whereas 1 divided by 0.004 is 250. So just a small change in P can have a great effect on this mean, this expected value. But how is the target value, mu0, set where the center line is? Either by just deciding what it should be, based on ideal specifications for our product, for example, or perhaps more commonly by using past sample data when the process was assumed to be in control. So suppose we draw m samples of size n. In the example we're going to do m equals 25 samples of size n equals 4 over a time period where the process is assumed to be in control. Denote the jth sample mean by x bar sub j. So there would be x bar sub 1, x bar sub 2, x bar sub 3, etc. up through x bar sub m. Then an unbiased estimator for mu0 is what? What would be intuitive? Well, how about just taking the average of the averages? Take the mean of the means, the mean of the x bars, add them up and divide by how many there are. In our textbook, the notation for this, you can see, is the mu sub 0 hat right there. It's an estimator for mu sub 0. And yeah, this is an average. Add up those xj bar values and divide by how many there are. This is a mean of means, sometimes called a grand mean. Isn't that beautiful terminology? Let's talk about variability as well. Let capital R denote the sample range random variable for samples of size n greater than 1, so 2, 3, 4, 5, etc. Okay, so this is a random variable that will vary from sample to sample as well. It's going to have a distribution. We might wonder what the mean of that distribution is, for example. And remember what a range is. It's the biggest number minus the smallest number for these quantitative variables, the max minus the min. Here is a relationship in 3 different forms between the expected value of R, which I could have written as R bar, and in fact I will write it as R bar here in a bit, and sigma, the standard deviation of X itself. The ratio of the expected value of R to sigma is constant d2, although that constant really depends on a fixed value of n, so I'm also specifying that it depends on n. For my students in our book, they just call it d2, and in many other books they do in fact as well. But I'm trying to emphasize it does depend on what n is. The sample size has an effect. But for a fixed sample size, this is a fixed number. If you, for example, multiply both sides of this equation by sigma and divide both sides by d2, you'll get this form. And if, for example, you take that equation and multiply both sides by d2, you'll get this form. Okay, so these are all equivalent to each other. It's this middle one that we're going to focus on here in the next slide or two. Here, by the way, are some approximate values for d2 of n. You can look these up. d2 of 2, if your sample size is 2, this thing called d2, why do they call it d2? I'm not sure. Okay, it's just notation that somebody picked somewhere. Is there a d1? Well, we're not going to talk about that. If the sample size is 2, d2 of 2 is 1.128. What would that mean? That would tell you the expected value of the range is about 1.128 times bigger than sigma. When the sample size gets bigger, the value of d2 continues to get bigger. d2 of 3 is about 1.693, d2 of 4 is about 2.059, and d2 of 5 is about 2.326. Does that make intuitive sense? Well, bigger sample sizes are going to give you probably more variability in the numbers you actually get. The max minus the min, the range, should be bigger on average. And yeah, by the time n is 5, you can expect the mean of R, the expected value of R, to be about 2.326 times bigger than sigma. And in fact, maybe based on what you've learned in the past, this would make sense. As n continues to get bigger and bigger, these d2 values tend to get a little bit higher than 4 in the long run, okay, as n goes to infinity. Before looking at the formulas for the LCL and UCL, lower control limit and upper control limit, let me exit out of the PowerPoint and go to this computer program called Mathematica to illustrate where the d2s come from. So don't worry about the details of the Mathematica. Just worry about understanding the big picture of how this is related to the d2s. I'm going to be generating data sets with something called a random variate and also normal distribution with a mean of 0 and a standard deviation of 1, which also means the variance is 1. And for each data set, I'm going to be computing the range by doing max minus min. That's what this means here, effectively. The fact that random variate and normal distribution are inside here twice means I'm going to be looking at samples of size n equals 2, but m is going to be 1,000. I wanted to make that very large so that I get decent estimates here. I'm going to be computing the range with this range function applied to these data, and then I'm going to be computing the mean. That's the big idea. So I get 1.145 the first time I try it. Let me try it again. Get a different number, 1.113. Again, 1.512 approximately, 1.146, 1.095. I should get different numbers each time because of the random nature of these things, but they're all in the ballpark of, you might say, 1.12, 1.13, something like that. Hey, and look back here. d2 of 2 is 1.13 approximately. That's not a coincidence. Let's try it when n is 3 and m is still 1,000. Once again, I'll be computing the means here. Every time I do it, now I get a number close to 1.6869, 1.7 or so. What is D2 of 3? Close to 1.7, 1.693 there. What if n is up to 4? I've got 4 random variates in here now. I get numbers a bit bigger than 2 typically, it looks like. D2 of 4 is a bit bigger than 2, 2.059. Finally, if I do it for samples of size n equals 5, I get means that are slightly above 2.3, it looks like typically. And D2 of 5 is slightly above 2.3, 2.326. Okay, so that's illustrating that these numbers seem approximately right. It's certainly no proof, but seems reasonable. Now let's go back to the PowerPoint and talk about the formulas for the LCL and the UCL. We're going to use the sample ranges to help us estimate the standard deviations and then do the 3 sigma approach, multiply by 3. Not the standard deviation of the population, but the standard deviation of x bar. We're going to divide by square root of n as well. So let's use m sample ranges, R1 through Rm, to estimate sigma. How? First, compute the observed value, this is a mouthful, of the estimator for the mean sample range. What's the mean sample range? That's E of R, the expected value of R. For fixed n, that's going to be a constant. This symbol right here is really a variable. R bar is an estimator for E of R. E of R is an average, it's an expected value. Why don't you just average the individual R's? That's what I'm doing here. I'm adding them up and dividing by the number of numbers that, or variables that I have here. Okay, so and then I would observe a value. In the abstract, this is a statistic, which is a random variable, but then I can observe these individual sample ranges and then compute this mean range. Next, compute the observed value of the estimator for sigma. And what would that be? It's based on the D2s. Sigma, remember, was E of R divided by D2. So sigma hat, your estimator for sigma, would be R bar divided by D2 because R bar is an estimator for E of R. Finally, divide sigma hat by square root of 3 and multiply by 3 and do a plus or minus effectively to get the LCL and the UCL. We need a point estimator for mu 0 as well, which is mu 0 hat. Minus 3 times your estimator for sigma sub x bar. And for the UCL, we do plus 3 times your estimator for sigma sub x bar. Now, again, with technology, you really can just use the standard deviation in your technology to do this. But based on the historical practice of using ranges, we can replace the sigma hat with R bar over D2 in that spot and also over here. And that is certainly easier to do by hand quickly if you don't have access to technology readily available. You can certainly use this approximation. You would have to have the value of D2, but the R bar would be a bit quicker to calculate than a standard deviation. There are also range control charts, which once again have lower control limits and upper control limits, though I should say the lower control limit is often 0 by default. We'll see here in a minute. We want to control the variability of the variability. So far we talked about controlling the variability in x bar itself, the variability of the mean. R and also sigma are measures of the variability itself. We'd like to control those numbers, the variability of the variability. We can make another kind of control chart. You could also call it Shewhart. It's an R control chart, a range control chart, instead of an x bar or mean control chart. Not going to go through all the theoretical details. I'm just going to jump right to the answer. Turns out, when sampling from a normal distribution, the LCL, lower control limit, and UCL, upper control limit for R, for an R control chart, are these numbers here. Mu hat plus or minus 3 times sigma hat. Mu hat sub r is an estimator for the mean of r, E of r. Sigma sub r hat is an estimator for the standard deviation of the sampling distribution of r. Replace mu sub r hat with just r bar. We could have called it that from the start. Replace, here's something new, sigma sub r hat with this expression right here. D3 divided by D2 times r bar. Yikes, another D. What's D3? Okay, we're not going to get into a ton of details other than just to say, here are some special values. D3 of 2 is 0.853. When your samples are of size 2, this number in the numerator is 0.853. D3 of 3 is about 0.888. D3 of 4 is about 0.880. D3 of 5 is about 0.864. Interesting. D3 goes up at least at first before it starts going back down a bit. Don't worry about what D3 represents, just be able to use it in this formula. We could compute these ratios as well. We could compute D3 of 2 divided by D2 of 2, and it's about 0.756. D3 of 3 divided by D2 of 3 is about 0.525. You can check these. D3 of 4 divided by D2 of 4 is about 0.427. D3 of 5 divided by D2 of 5 is about 0.371. So, as the sample size gets higher, this number D3 divided by D2 is generally getting smaller. Bigger sample sizes mean less variability in your statistic. That makes intuitive sense. And once again, we're alerted to the process being out of control if the observed value of R, the range based on a certain sample of size n, is outside the LCL and UCL control limits. Oftentimes, like I mentioned at the beginning here, we actually use 0 for the lower control limit, because sometimes with this formula, when you do the minus, you actually get a negative number. But ranges can't be negative. Oftentimes, r bar minus 3 times sigma r sub r hat is negative. In this case, take LCL to be 0. In other words, LCL is really not this thing with a minus sign. It's really the maximum of this difference and 0. That's really what LCL is in this context. All right, take a breath. Let's do an example. Although before we do the example, I quickly want to mention that in here, I have code that can compare the standard deviation of the ranges, sigma sub r, with D3 divided by D2 times an appropriate standard mean up here. For example, this 1.09528. Let me just do the first one here. 1.09528. That's the mean of the ranges. That's r bar. 0.756 is D3 divided by D2 when n is 2. 0.756 is the one right here. If I multiply those, I should get something that's close to the standard deviation of the range data. Your estimate of sigma sub r. Yeah, these numbers are fairly close. Okay? So I wanted to do that as well. All right, let's look at our real-life example. Manufacturing O-rings. A manufacturer of synthetic O-rings must monitor and control their dimensions. How big are they? O-rings are used in numerous industries: medical, aerospace, oil refining, automotive, chemical processing. There's tons of applications of O-rings. A certain type of O-ring is specified to have a diameter of 2.612 inches. Okay, we're using inches here. We probably would have been better to use something in centimeters, within certain tolerances. What we want to do is we want to set up a control chart for future use in detecting when our manufacturing process is out of control. 25 subgroups, or samples, in other words, M equals 25, of O-rings are looked at over a certain amount of time, each with a sample size n equals 4. In each case, for each one of those 25 subgroups or 25 samples, x bar, the sample mean, and r, the sample range, are computed. Here's the data, okay? Now it's too much to just look at and try to glean a ton out of this, except to note that pretty much all these numbers are close to 2.60 or 2.61. or perhaps 2.62. Very rarely are they under 2.6. I do see one number under 2.6 right here. I think I saw another one somewhere over here. These are 25 subgroups, 25 samples, each with 4 data values. Across each row, I want to compute x bar, the mean, and r, the range. We'll go to a spreadsheet to look at this, although let's look at the graphs in the end here before we look at the spreadsheet. Here are the results as graphs, control charts. Here's our control chart for the mean, my x bar chart. The sample number, the subgroup, is across the horizontal axis. There'd be a first one, then a second one, then a third one, etc. The sample mean, x bar, in inches, is the second coordinate of these points. And look, it looks like we have one observation that's just barely out of control, just barely below the LCL. By the way, in the spreadsheet, we will show where these numbers come from, both the CL, the center line, the LCL, and the UCL. But we also want to look at controlling R itself. We can create an R control chart for the range. Once again, we have a sample number along the bottom. Sample range here. Notice the bottom is at 0. Okay, the LCL from the formula ended up negative in this situation. Once again, we end up having one of these out of control. Now remember, what we're using these for is we're using these for future use. And so what probably would be better to do, and what is sometimes done here, is just essentially throwing out the ones here that are out of control. So we throw those out and make a new control chart and compute new LCL and UCL based on throwing out the one data point, or maybe the 2 in this case, where things were out of control. That is something some people sometimes do. Let's end by looking at a spreadsheet. Now, it took me a while to set up the spreadsheet, so I'm just going to highlight some things. So the sample or subgroup is this column here, 1 through 25. X1 through X4 for each one of those samples. These are just the data here. I used equals average to compute the mean across each row. These are the X bar values. And I can copy and paste that formula to get 25 values of X bar, these numbers here. And I can also compute, similar to what I did in Mathematica, max minus min. Max B3 through E3 minus min B3 through E3 computes the range for that first row. And you could copy and paste that downward to compute the range for the other ones. We want the means of these things. We want the grand mean, for example. The mean of the means is the grand mean. I averaged F3 through F27, the numbers in the sample mean column. The X bars get averaged to get this grand mean, 2.607216. And I can take the average of the ranges in column G to get the mean of the ranges. R bar, an observed value of R bar. Here I made a table of values of the D2 and the D3 and the ratio D3 divided by D2, though in reality here, since for us n equals 4, we're only going to use this line right there. And I computed, for example, R bar divided by D2. You can see up here it's B3 divided by B35 divided by E35. This number, R bar divided by D2. 3 times that gives me 3 times sigma hat over square root of n. I also have to divide by square root of n, which is square root of 4 here, which is 2, of course. And now, for the LCL, CL, and UCL, I use this thing, the mean of the means, the grand mean, plus or minus 3 times sigma hat divided by square root of n, which is this number, to get this. You can see the formula for this one is equals B3 plus B41. Here's B33 right there, plus B41 right there. This one is just B33. This one down here is equals B33 minus B41. And I can do it for the range as well. This is for the control chart of the range. This is 3 times D3 over D2 times R bar right here. Notice the formula is 3 times G35 is right here, times B35 is right there. And then I take the R bar itself and add this number right there to get this number, B35 plus F41. And down here I got a 0, but I actually programmed it to give me something positive just in case. The R bar minus 3 times this thing was positive. I did a max of this thing, B35 minus F41, comma, and 0. Put a comma 0 in there. In these columns, I made the LCL, CL, and UCL for the mean, and also for the range. And then it's a matter of highlighting the appropriate columns, inserting chart, and picking an appropriate chart. You want a line chart. Don't worry about what I want to get rid of that. To ultimately compute these charts here, the control chart for the mean and the control chart for the range, just like I showed you in the PowerPoint. That's it. That's the basics of control charts when we're doing process control, which is a part of a larger subject of quality control. Thanks for watching.